this video, we're going to be talking about how to solve for variables in congruences. Now, before we get started, I want to make a very important point here that we are not technically solving for variables. That's what we call this, but technically when we're solving for x, we're getting a solution for x. That solution doesn't vary, and so it's really hard to call it a variable. It's more accurate, it's more technically correct to call it an unknown that doesn't vary. It's a constant, it's not a variable, but we are going to be solving for x in congruences. And now that we have some algebraic rules to govern congruence relations that we've developed over the last few videos, we can attempt to solve for an unknown in a congruence. So for example, is there a value of x that satisfies 3x plus 2 equals 4 mod 5? And if so, what is it? Well, in this example, since the modulus is small, we could simply try every possible value for x. There are really only 5 to consider though, since any integer that satisfies the congruence could be replaced with any other integer it was congruent to, modulo 5. Here, when x equals 4, we get that 3x plus 2 is, let's see, that would be 14, which is congruent to 4 mod 5. This means that x equals 9 and x equals 14 and x equals 19 and so on will each also be a solution because, as we saw earlier, replacing any number in a congruence with a congruent number does not change the truth of the congruence. I want to clarify that is for only linear problems, things like ax plus b equals c. So in this example, simply compute 3x plus 2 for values of, if you wanted to solve this, you would just compute 3x plus 2 for various values. Let me erase this. And the point here is that x is going to be some element of the set 0, 1, 2, 3, 4. So just test 3x plus 2 with all 5 of these options. And this will give, if we plug it in, this gives, that's supposed to be an arrow, there we go, 2, 5, 8, 11, and 14. That's 3x plus 2, and then only 14 is congruent to 4 mod 5. Let's also see how you could solve this using our rules for the algebra of congruences. Such an approach would be much simpler than the trial and error tactic if the modulus was larger. If there were a lot more opportunities for x to be different values, then this could easily become a very challenging problem. So let's try to solve this algebraically. First, we know we can subtract 2 from both sides. That's not a problem. So we could subtract 2. And we get 3x is congruent to 2 mod 5. Then, to divide both sides by 3, we can't really do that. Yes, 2 divided by 3 is 2/3, but we're not in the rationals numbers world. We're in the integers world. So the number 2/3 isn't quite a solution because the number 2/3 doesn't really exist. So we're actually going to instead add 0 to both sides. And I know you might say, well, adding 0 does nothing. On the contrary, it technically does work if we add 0 to the right-hand side, but that 0 is going to look a little different. We're going to add 0 on the right side. 10 is 0 mod 5, and so I can add 10 on both sides. If I add 0 on the left side and 10 on the right side, I'm adding the same number to both sides here. 3x plus 0 is 3x, and 2 plus 0 is 2, but also 12 mod 5. Okay, and now I can solve by dividing both sides by 3. Now, it's important that when we divide both sides by a number, if that number is not relatively prime to that number right there, the modulus, then you have to be very careful with how you divide. And we've done a video on this discussing that in a previous video. But in this case, 3 and 5 are relatively prime, and so we can actually divide both sides by 3 to get that x equals 4 mod 5. Let's get a better 5 in there. There we go. Now notice that this in fact gives the general solution. Not only can x equal 4, but x can be any number which is congruent to 4. We can leave it like this, or we can write, for example, x equals 4 plus 5k for all k in the integers. Hey everyone, real quick, I just want to mention that this video is a part of a whole course that I made. You can find a link to this entire course in the description below, and make sure to click on that subscribe button. All right, let's do an example together to see what this looks like all wrapped up in one example. And we'll move a little bit faster. So in this case, we're going to be solving 7x congruent to 12 mod, let's do 13. Okay, so again, there are two ways to approach this. You can first guess what x is, guess and check. There are only 13 options for what x could be. It could be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Those are all of the options that x could be. So try them all and see which one works. But because 13 is a larger number here, that's probably not a reasonable strategy. So instead, we're going to try to add 0 on both sides. Now, I want to mention there actually is a faster way of solving this using the extended Euclidean algorithm, but I probably would not recommend that algorithm because A, it's beyond the scope of discrete math, and B, I really don't want to teach a bunch of extra number theory to help you solve a problem that could probably be solved without the extended Euclidean algorithm. So I'm going to add 0 on both sides. On the left side, I'm going to add that kind of 0, and on the right side, I want to add a 0, but some other version of 0. And I want to make it so that the right-hand side is divisible by 7. My intention here is to divide by 7 and not get a fraction because we're not in fraction world, we're in integer world. Now, what numbers are equivalent to 0? Well, there's 0, but that doesn't really help me. I can add 13, which is equivalent to 0. I can add 26. I can add 39. I can add, and so on. And so let's try adding multiples of 13 to 12 until we get a number that's divisible by 7. So there's 12 plus 13 is 25, plus 13 is 38, plus 13 is 51, plus 13 is 64, plus 13 is 77. There we go. So 12 is equal to 77 if we add 13, how many times? Let's see here. 1, 2, 3, 4, 5 times. So I'm adding 13 times 5, which I believe is 65. I'm adding 65 to the right-hand side, but keep in mind, 65, is that right? Yeah, 65 is equivalent to 0. So I'm adding 0 on the right side here. And so this means that 7x is congruent to 77 mod 13. Okay, that helps. That helps a lot because now I can divide both sides by 7. Now, before we divide, we have to make sure, is 7 relatively prime to 13? The answer is yes, and so I can, in fact, divide both sides by 7 to get x equals 11 mod 13. Now, how do we know we have the right answer? Well, we should be able to check. Is it true that 11 times 7, or 7 times 11 is congruent to 12? Well, 7 times 11 is 77, and then we can subtract 13 over and over again. Or you could do the division algorithm, dividing 13 into 77, and I believe 5 here is the number we would throw in, and 5 times 13 is 65, which leaves a remainder of 12. Exactly the remainder that we would want to have here. Anyways, that's this example. Thanks everyone, and I'll see you in the next video.